Hello everyone, welcome back to another video. In today's lesson, we'll be going over the AP Physics topic of dynamics. First up, what is dynamics? Dynamics is the study of the forces that cause objects and systems to move. It is associated with forces, acceleration, and mass. The key concepts we'll be going over today is the concept of force, Newton's third laws, free body diagram, the different forces, and the vector of forces. First, let's begin with the concept of force. You might ask yourself, what is a force? A force is an interaction between objects that creates acceleration. You can treat it as a push or a pull, and there are actually many different types of forces. For example, there's gravity, there's support, which is also known as normal force, and there's friction, and there's spring forces. You can treat dynamics as this idea of forces, and forces is what cause acceleration. And we all know that acceleration is what leads to a change in velocity and a change in the object's position. So forces is really the root cause of why things move, but also how things move and in which direction do things move. Let's begin our lesson really with Newton's three laws of motion. The first law is a body at rest remains at rest, or if in motion remains in motion at a constant velocity unless acted on by an external force. Here, I have shown you a free body diagram. We'll be talking about this later on in the video. However, I want to show you guys here is that this object right here, the red box, is experiencing four forces. There's two forces vertically and two forces horizontally. We can see from the length of the arrow that the vertical forces are the same in magnitude, so they cancel out each other. The one to the left is shorter than the one to the right, so it means the object is experiencing a net external force to the right. And since a net external force exists in this scenario, this object does not stay at rest or stay in constant velocity motion because there's a force that's acting on it. Now let's talk about Newton's second law. Newton's second law states that the acceleration of the system is directly proportional to and in the same direction as the net external force acting on the system, and is inversely proportional to its mass. Or we can use the expression A equals F over m, or rearranging the equation F equals ma to represent this. Let's look at it more closely. From this first equation, we can see that the force of the object divided by the mass of the object is what gives us acceleration. If the mass is heavier, then the acceleration will be smaller. If the mass is smaller, the acceleration will be higher. And this actually explains why. If we're pushing a basketball and a car with the same amount of force, the basketball actually moves faster because the acceleration is higher due to the lower mass. The car, on the other hand, with its high mass, will actually accelerate slower. Now let's talk about Newton's third law. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to this force that it exerts. I like to picture this with the this idea of pushing a wall. When you're pushing a wall, you are exerting a force on the wall. However, your hands are hurting, and this is because the wall is actually exerting a reaction force back at you, and this is known as an action and reaction force pair in Newton's third law. And we can see that from this expression and also from the diagram visually that the two forces are opposite in direction. Now let's talk about a free body diagram. Free body diagrams are diagrams that explicitly represent all the forces applied to an object, used to analyze situation depicted by the question. For example, in this first image, we can see that there's an object lying horizontally on a slanted surface, and we can see that it's experiencing three forces, and I actually drew these forces out for you already. There's Fg, there's Fn, and Ff. Fg is the force of gravity, Fn is the normal force, and Ff is the force of friction. Let's look at the gravity first. Gravity for an object, it will always be vertically downwards. So regardless of what object you're looking at, it will always be vertically downwards. Normal force is always perpendicular to the surface. It is this concept that the surface is providing a support to the object and making sure the object stays on the surface. So this force is always perpendicular to the surface. And then there's the force of friction. We'll be talking about this in the future video, and don't worry about it right now. Let's look at the diagram on the right. We can see that when this professor is pushing a cart, for the professor herself, her foot is grabbing onto the ground and she is walking forward. When she's walking forwards, her foot is actually pressing on the floor backwards to the left, and the floor exerts a reaction force to the professor, allowing her to move forward. When she's pushing the cart, it's similar. She's exerting force on the cart, however, she's also experiencing a resistance from the cart. This is because the cart is exerting its reaction force on the professor. We can also see that the cart's wheel also experiences friction. Now let's talk about the different forces. The most common forces we'll need to calculate in AP Physics are weight, normal force, friction, tension, and spring force. We'll be exploring spring force later on in oscillatory motion, so you don't have to worry about it right now. Let's begin with the force of gravity. We know that an object in midair will fall, and this is because of Earth's pull on the object. The equation of the force of gravity gives us an idea of how strong this force really is. Let's look at the equation. Force of gravity can be represented by Fg, and it is calculated by m times g. M is the mass of the object in kilogram, and g is the gravitational constant, which is 9.81 in every single question you will be doing. However, I just want to tell you guys that the acceleration, this gravitational acceleration actually changes depending on where you are relative to Earth's center. If you're very far in the atmosphere, then this g will be lower, and if you're right on the surface, it will be high. And you only need to know that this value is 9.81 meters per second squared. Now let's talk about the normal force. We know that an object always experiences the force of gravity. However, why is an object placed on a table not moving? Let's look at this image on the right. We can see that there's the weight of the object, the Fg, which is also the mass of the object times the gravitational acceleration of 9.81. However, there's also the normal force from the table that's exerting onto the pillow. And we can see that these two forces balance out, and that's why the object is not moving. So therefore, normal force is actually the same in magnitude as the weight of the object or the force of gravity. However, keep in mind that normal force are not a action-reaction force pair with weight. Now let's talk about tension. Tension is a force along the length of a medium, especially a force carried by a flexible medium such as a rope or a cable. We can see that here there is a rope and it's holding an object with the mass m. This m is experiencing a force of gravity because it has mass, right? So the weight is the force of gravity of the object. There's a tension between your hand holding it and the mass here, and we can see there's tension within the rope. This free body diagram shows the forces the mass is experiencing. It has a tension going down, a tension going upwards because of the string holding it upwards, and there's also the force of gravity pulling it downwards. Now let's talk about the forces represented by vectors. Similar to velocity, forces can be represented by vectors, and it is very important. Let's consider the very basic example of a slanted surface. There is a skier on the surface, and the skier really, it could be a box, could be a ball, it could be anything on a surface. And we know that the weight or the force of gravity always goes downwards like this. Normal force is perpendicular to the surface, and the force of friction is going backwards. Now, we want to analyze the situation. So let's think about breaking this weight into into different components. We can, in most cases, we'll be breaking forces into the vertical and horizontal components. For example, in here, using trigonometry, we can see that the weight of the force of gravity going down the mountain is actually sine 25 degrees multiplied by the weight. The component that's vertical to the surface is the cosine 25 degrees multiplied by the weight. Let's look at an example question. Consider this diagram where it shows the skier skiing down a mountain. Her total mass, including equipment, is 60 kilograms. What is her acceleration if the force of friction is negligible? Let's first look at the free body diagram. We can see that the forces are listed here, and since in part A, force of friction is negligible, we can ignore this small component here. We can separate the weight into vertical and horizontal components. We know that this person is only moving down the mountain because she is not moving up and down, right? She's skiing, she is not just jumping, whatever. So therefore, we only have to consider this horizontal component of the weight, and this is the force that is causing the acceleration. We know that acceleration can be calculated using F divided by m. So therefore, if we calculate weight multiplied by sine 25 degrees divided by 60, we can get the acceleration of the person. In this part B, we know that the friction is known to be 45 newtons. To solve this question, it's still very simple. We use the horizontal component of the force minus the 45 newtons of friction, and using this new net force divided by 60, and we can find the acceleration. These are all I have today for you guys, and thank you so much for watching.